Okay, so today's speaker is Zhenyi Wang from University of Maryland College Park, and he's going to, the title of your talk is, yes, read the title.
Okay.
Okay. All right. Building adaptive and resilient AI, bridging continual learning and model extraction.
Thank you for your introduction. Before I dive deeper about my research presentations, I will first briefly overview of my research. So in current days, the AI is growing very rapidly. Its goal is to achieve a human-level intelligence. The approach is mainly data-driven. However, existing machine learning or deep learning, they assume that the data is perfect. That is, they want to learn from perfect information. The first assumption is that they assume we have a large amount of high-quality data. The second assumption is that the data distribution is static and not change over time. The third assumption is that the test data distribution is the same as the training data distribution. However, in practice, the training data is imperfect. So this move to my research contributions. The goal is to learning from imperfect information. So to address the first challenge is that in many real applications, we only have a limited amount of training data. For example, in the medical field, we only have a very limited amount of data. The second challenge is the training data distribution shift over time. And in these directions, I build approaches on the continual learning. The third challenge is that the test data distributions are very different from the training data distribution. And in many cases, the test data may be unsafe. So in this direction, I focus on the trustworthy ML. So in my long-term research goal is to build a reliable, efficient, and adaptable AI. So my research involves these three research directions: continual learning, data efficient learning, and trustworthy AI. And they also have some interplays between these research directions. For example, my research in continual learning also benefit from trustworthy AI. And my approach in trustworthy AI also borrows approach from continual learning. So these research directions are mutually beneficial to each other. And in today's presentations, I will select a subset of my research results in recent years. For example, in today's presentations, I will discuss continual learning and trustworthy ML. And I will build their connections from the continual learning. Now let's move to today's presentation. Is about building adaptive and resilient AI, building bridging continual learning and model extraction defense. So first, in nowadays the machine learning is a static process. That is, we train on a static data set, and after that, we deploy the models. But in practice, the data distributions and the environment may change over time. So we need to continually learn from this non-stationary data distribution and the environment. So we need to learn the models from the new data and then gradually deploy the models over time. That is, this process is a dynamic process. And my research is actually focused on the adaptive ML to gradually adapt it to the changing environments. These research directions also borrows the ideas from the human learning, because as we human beings, we often build our knowledges on the previous one, and we do not start training the models from scratch. Instead, we may learn the skills incrementally over time. For example, in this case, we may learn how to read books, write papers, perform math tasks, and then play basketball and cooking. So the continual learning is to simulate the human learning process by incrementally learn the task and knowledge over time. So we can conclude that traditional static machine learning is clearly not enough to build a real-world AI. There are many real-world scenarios to illustrate this point. First is we need the learning system to dynamically adapt it to the changing environment. For example, in the autonomous driving system, we may need to let models adapt it to the changing environment. For example, the weather, the road conditions, and the traffic regulations may change across different cities. The second is in the on-device learnings, we only have a limited amount of computing resources and also may have limited memory buffer. So we cannot store all the previously learned data set on the edge device. We need to incrementally learn the new data set. The third reason is about the data availability. So in nowadays, the large pre-trained models, they train on large scale data set. Among these data set, they contains many copyrighted data set and also may contains of private data set. So after they release the pre-trained models, these data sets are not released. So we need to incrementally learn the knowledge over time. Now let's see how can we address this challenge. One promising way to achieve this goal is through the continual learning. The goal of continual learning are twofold. The first is to adapt it to the sequence of tasks over time. This is also known as incremental learning. The second goal is when the models adapted to the new task. We also want models to remember previously learned knowledge. For example, in the first stage, we classify two classes. And during the second stage, we incrementally have another two classes. And during the third stage, we then have another two new classes. In existing continual learning approach, it can be categorized into several categories. The first is a memory replay-based approach. In these research directions, they allocate a small memory buffer, and then we replay this amount of data with a new task together to mitigate the catastrophic forgetting. The second is an architecture-based approach. In these directions, we dynamically update the network architecture to allocate the model capacity to different tasks. The third direction is a regularization-based approach. In these directions, we add a regularization loss term to ensure that the model parameters will not deviate from the previous optimal solution. The fourth direction is a subspace-based approach. So in these directions, we project a gradient into the orthogonal gradient direction. So by doing this, we have benefit that the new task gradient and old task gradient are orthogonal, so they don't have the mutual influence. Then we can mitigate the task conflict. The last one is a Bayesian-based approach. In this direction, they maintain posteriors of the model parameters, and then they constrain the posterior distribution of the model parameters not change much during the learning process. In real-world applications, continual learning can be applied to a wide range of real applications. The first is on-device learning. For example, we can use our cell phone to capture the image and then train the models on the cell phone without needing to send the image to the central server. And after that, we may use our cell phone to capture another image and then incrementally learn this new captured image over time. The second is we can apply continual learnings to the medical image segmentation. For example, we may incrementally have labeled data sets for different organs of the medical image. We may need to incrementally segment this image over time. The third application is we can apply the continual learning principles to the trustworthy AI. And this is my research directions. For example, nowadays, the machine learning can be provided as a black box API, and the users can access the APIs of service by sending their query data to the, for example, the ChatGPT, and then they can then get their returned results. However, the attackers can also send the query data to the ChatGPT and obtain its response. And over time, the attackers may collect a large amount of these data sets. And then they train stolen models has similar functionalities as a victim model. The similar functionality means that the stolen models is similar to the ChatGPT, but they may have different architectures and so on. In these research directions, I developed a serious work to address this trustworthy AI. Now let's see the technical challenges in continual learning. The first is called catastrophic forgetting. And I will use two-task incremental learning as an example. For example, for the first task, we train the models to minimize its loss functions on task 1. Then we start from this point to gradually move towards the optimal solution of task A. And after that, we may have another task B. Then we gradually update optimal solutions toward the task B. So if we look at loss functions, during this period, the task A's loss functions gradually decrease. And after that, since we have another new task B, its loss functions will gradually increase. This means that the task A's knowledges will be gradually forgotten. The second challenge is the trade-off between the new task and the old task. This is also known as the plasticity and stability trade-off. If we prioritize the new task learnings, we have excellent new task performance, but we may need to sacrifice the stabilities. This means that the old task knowledge will be gradually forgotten. On the other hand, if we prioritize the stabilities, that is, we want to keep the knowledge from the old task, but we may need to sacrifice the plasticity. This means that the new task performance will be sacrificed. So in the real-world applications, we need to trade off between these two factors and achieve the best overall performance across the entire task sequence. So in these presentations, I will first present my theoretical foundations for continual learning to discuss how can I address these two challenges. The second part is I will apply the continual learning principles to address the AI trustworthy AI challenges of model extraction defense. Now let's see the first part of my today's presentations about the foundations of continual learning, and to discuss how can I address these two challenges. So for the first challenge is how to address the catastrophic forgetting issue. In these directions, I propose a data-centric approach to address the forgetting issue. Now let's see, for existing works, the traditional memory replay, the optimized loss functions consist of the new task loss functions plus a memory buffer loss function. So the memory buffer loss functions, since it is repeatedly optimized, these loss functions will be over memorized and optimized. So this leads to the bias towards the memory buffer data. This is also called as a buffer-specific memorization bias. This issue leads to very bad performance on the previous task. To address these limitations, I propose a distribution robust memory evolution. The basic optimization is to convert the optimization into the mean soup optimization. The inner soup optimization is to optimize the worst case memory buffer data distribution. The outer minimization is to optimize the model parameters, and also subject to a constraint that the worst case memory buffer data distributions with respect to the raw memory buffer data distribution less than a small constant epsilon, and also subject the constraint that the raw memory buffer data gradient and the evolved memory data gradient is greater than a constant to ensure they have better similarity. However, to optimize these loss functions, we need to optimize over a function space, since the probability measure is a continuous optimization into a probability measure space. To address this optimization challenge, I will use the Wasserstein gradient flow to convert these min-max optimizations into a continuous optimization in the probability measure space. So the benefit of this optimization is that we can convert the optimization in the probability measure space by following this continuous update in the probability measure space into the Euclidean space. Since in the Euclidean space, it is much easier to optimize. Now, to instantiate this optimization, I designed the target probability measure as the energy function, and U is defined as the memory buffer loss functions minus this constraint. This is derived by the Lagrange multiplier, and then convert these optimizations into the reproducing kernel Hilbert space, also known as RKHS. Then we can obtain the update solutions for the memory buffer data. The first term is a smooth gradient term. This term is to weight the gradient in the memory buffers by their kernel functions, since the kernel functions represent the similarities among different data points. The second is a repulsive term, since the kernel functions represent similarities among different data points. So if we minimize the kernel functions, the effect is that we will make the data points becomes dissimilar. So this will encourage data points becomes more diverse. So to evaluate our approach, we perform experiments on various data sets, and we obtain the improvements across different data sets. In these tables, each number represents the overall test accuracy after we training on the last task. So that these numbers, the higher, the better. Now,
kernel DRO aspect there. So DRO is essentially built on a certain set of distributions.
yeah.
So where is that here?
So what do you mean?
So in distribution, your robust optimization, building an uncertain set of distributions.
Yeah.
Kernel, and then you're trying to solve, for example, a min-max problem or something like this, so that it becomes distribution in your robust.
Yes.
So where is that here?
Yeah, so here is we treat particles to represent the data distribution. So like in similar to the Bayesian sampling, we use particles to represent the samples from the distribution. So this here, the X represent the particle. And here, each Xi, suppose we have n particles. So this n particle represent the data distribution. By using the gradient flows, we convert the continuous probability measures into a discrete representation of the distribution. So here, actually represent the uncertainties in the neighborhood of the memory data buffer.
I mean, the word kernel DRO means.
So what kernel are you using? That is my question.
So can you go to the table? The table is there.
Here.
So what is DRO? Kernel, is that yours? Kernel DRO?
DRO means distribution robust optimization.
And what is kernel?
Kernel means to convert the
K is a kernel here, right?
yes, right.
Yeah, so he's saying is that is a particle distribution, like condensation and so on, right? So that can model any distribution as compared to like Gaussian and so on, right?
Yes, right.
Instead of Kalman filter, people use a particle filter, something like that.
Yes, right. Thank you. Okay.
I have another question. So this method we presented is supposed to help with the first challenge of not forgetting, right?
Yes.
Can you conceptually explain how it does that? How it helps you not forget what you've learned on task A when you have a new task? I was trying to.
Yeah. So here is actually represent to address the over memorization of the memory buffer. For example, in this case, the memory buffer data is clearly separated by repeatedly optimize the memory buffer loss function. So this is not good because it overfeed to the memory buffer data. So the how it helps is because by a smooth gradient and using the repulsive term, we can convert the representation of the data becomes more diverse and harder to classify. So this is to mitigate this over memorization bias.
But are you still storing storing some information from the previous task?
Yeah, right.
And where is that? Like, where do you do that in your equation? You just, how many samples do you store for each task?
So depends on the data set. So like for the small data set like Cifra 10, I set it to like 500 data points from previous data set.
So this method, they just store this one, and that's what memorize it. He's saying the typical method where they store there's some problem, so this whole thing is fixing that, right?
Yeah.
That's what the idea is.
Yeah, so the basic is based on like we store some information and we mitigate the over memorization to further improve it.
And when you got the.
Yeah, very, thank you.
Okay.
The kernel methods are very much controlled by the amount of samples, like memory. When you say memory evolution, what it actually means, you collect more samples to make the function work better.
Yeah. Great question. So this means that the memory buffer itself at a specific time point, it is fixed. But the memory evolution means that given this fixed memory buffer data, we transform the data representation and also change the raw data itself to another new data point. So by training on this transformed data, it will mitigate the overfitting or over memorization. Yeah, it's the same. Sorry. Memory evolution is that given a fixed like static memory buffer, suppose that like at t equal to 10. At this point, the memory raw data is fixed, and during this time point, we gradually evolve the memory data to another data distribution. It's close to the original raw data, but it's different.
Number of memory bits are fixed, but it's transforming them to the vector representation as compared with the storing.
Yes, right. Yes. Okay, let's continue. So now let's discuss how to address the second challenge. The second challenge is about the trade-off between the new task and old task. In these directions, I develop a model sensitivity reduction for continual learning. Now let's see the technical challenge. In these directions, in continual learning, we face a trade-off between the old task and the new task performance. As we discussed earlier, if we prioritize the old task performance, we will sacrifice the new task performance. But if we prioritize the new task performance, we may need to sacrifice old task performance. So in these papers, my research will address this trade-off by simultaneously improve both the old task and new task performance. To address these challenges, I view this problem from the parameter sensitivity perspective. This is because in continual learning, if the parameter is very sensitive to parameter updates, it will quickly forget previously learned knowledge. The second disadvantage is that if the parameter is too sensitive, if we train the models on the new task data, it will easily overfit to the new task data. So to address this trade-off, we can achieve this goal by reduce the parameter sensitivity. Because if we reduce the parameter sensitivity, when the model adapted to the new task, the previous learned task data will not be quickly forgotten. And also, since the parameter is not very sensitive to the parameter updates, the overfitting to the new task will be reduced. This means that we can simultaneously improve both the old task and new task performance. Specifically, the optimization method is to minimize the worst case continual learning performance within a distributional neighborhood. So let's say in traditional continual learning, the loss functions can be viewed as this form. The first loss functions is a loss on the new task data. And second is a loss functions of the forgetting mitigation loss. The forgetting mitigation loss can be viewed as such as regularization-based loss functions, and also like the memory buffer replay loss functions, also for the like gradient projection loss function. However, as we mentioned before, simply optimize these loss functions will lead to the trade-off between the new and old task performance. So to address this challenge, my approach is to optimize the worst cases continual learning loss function by subject to the constraint that the KL divergence between the worst case parameter distributions with respect to the current parameter distribution. So this ensures that the worst case parameter distributions will not deviate from the previous one. By converting these like constrained optimizations into the following unconstrained loss function, so we can convert it into this optimization goal. The U and V just denote the density functions of U and V. To optimize these loss functions, I choose a natural gradient descent approach. So the natural gradient descent approach is just to add a Fisher information matrix condition to adjust the learning process. So because the Fisher information matrix represents the parameter-wise importance for each parameter. But the NGD is a very costly operation because the Fisher information matrix calculation. So the solution is that we can apply the dualities of the natural gradient descent for the exponential family distribution. The following theorem means that the natural gradient in the natural parameter space is equal to the gradient in the expectation parameter space. So the benefit is that if we view this equation, the red part of the natural gradient can be converted to the gradient in the expectation parameter space. So we don't need to calculate the Fisher information matrix in the expectation parameter space. This will significantly improve the running efficiency. Now let's see how to instantiate this optimization. We set the U and V as the Gaussian distributions with the diagonal covariance matrix, and then we plug in this diagonal covariance matrix to obtain the worst case U and sigma for the worst case Gaussian distribution. To further analyze these optimizations, we perform like theoretical analysis under some assumptions. So if the worst case CL loss functions within a distributional neighborhood is equal to the expectation of the continual learning loss functions plus variance of loss function. So the first term is a standard continual learning loss function. The second term is additional benefits to minimize variance of loss function. So the benefit is that if the loss variance is very high, this indicates that the continual learning loss is very sensitive to the parameter updates. If the variance is small, it means the continual learning loss functions is not sensitive to the parameter updates. So by minimizing the worst case CL loss functions, we can implicitly minimize the loss variance. So this indicates that we can actually indeed minimize, reduce the parameter sensitivity. Then we evaluate the model's performance across a different data set under both the task incremental learning, class incremental learning, across like different data sets. So each number represents the overall test accuracies after the last task. And we can observe that across different data sets, our method can improve its performance across in different scenarios. And also evaluate the new task performance. So during the inter-task sequence, we reduce the parameter sensitivities for different model parameters, and we can find that it also increases the new task performance. So empirically, this also supports our finding that by reducing parameter sensitivities, we can both improve the new task and old task performance. In addition to this, works in foundations of continual learning, we also have works on the continual learnings in foundation models, such as the vision transformers and the large language model. So in the vision transformers, we insert like different the task invariant prompt and the task specific prompt in each tension layers by capture the task invariant knowledge and also for the task specific knowledge. Due to the time limits, I only like briefly summarize this approach and evaluate its performance on the COB200 and ImageNet R with like a large scale vision transformer as a backbone. So the orange line represents the performance of our approach. Like we can observe that across the entire task sequence and different learning sessions, our method achieves the overall best performance across different data sets.
This thing, right? You are using the prompt, right?
Yeah, right.
And so then this is in addition to your change of distribution, evolving memory and so on, right?
Yeah.
These prompts are learned, these are learned from. Like,
Yes, right.
So there's this method we were looking at called dual prompt or something, you know, about that. This method where we use two prompts.
Yeah, so the prompt, it consists of task invariant prompt.
Yeah, that's right.
Yeah. Yeah, this prompt is trained on the first like incremental session. The second is a task specific prompt. This is to adapt to the like new task.
Okay, yeah.
Thank you. Now we summarize the first sections. I propose both a data-centric approach and a model-centric approach to address the two challenges in continual learnings, including the catastrophic forgettings and also the trade-off between the new task and the older task. In the next section, I will discuss how to apply the continual learning principles to address the trustworthy AIs and also the AI security problems. This is because nowadays pre-trained models, they face evolving like security threats. So the benefits of view this to defend against these security threats is that we can continually enable the pre-trained models to have more like defense capabilities against these AI security threats, and also have the models to retain their previous knowledge. Now let's move to the second part. Is to view the model extraction defense from the perspective of continual learning. The research background is that for currently the pre-trained foundation models is very expensive. For example, for the Google Gemini, they cost like more than $191 million to train the models. But attackers may want to steal these like black box models in the API. This is because if the attackers steal this black box API, they can convert this black box API into a white box model. The white box model can obtain all the information, such as they can have their own network architectures and model parameters. They can use these white box models to perform more effective attack against the original like black box API. And also they can use this white box model to extract like some like private information from the white box model, such as they can use the model inversion attack to further inverse the pre-trained data sets. So as we discussed previously, the model extraction attack, also known as the model stealing attack, is to train stolen models has the similar functionalities as a victim model. As we discussed previously, the attackers may want to train like a similar ChatGPT as a original black box ChatGPT. They have a similar function as the original one. So now let's see the threat model and how attackers to perform this attack process. So first, they have a large amount of unlabeled data set. Then they send this unlabeled data set to the black box target model, such as ChatGPT, and then they return their prediction response for these unlabeled data sets. And after that, they can use constructed data sets to train a clone model. The goal is to make these clone models has similar functionalities as this black box target model. However, the defenders may want to defend against this kind of stealing behavior. The goal is multifold. The first goal is to protect the functionality. That is, we don't want an attacker to steal the functionality of the model. We want to minimize the clone model's performance, such as its accuracies or some other like evaluation metrics. The second is the model architecture itself is also expensive. For example, in the Meta's their recommendation system, they have their internal architectures to make effective recommendations. These kind of architectures needs lots of training data and hyperparameter tunings to achieve the best one. The third one is we not only want to defend against this kind of stealing behavior, but also we want to maintain the performance against maintain the performance for the benign user. Since the benign user's performance is actually what we want, and we need to guarantee the service quality. So the changes in existing model extraction defense is that the existing works can be classified as active defense and passive defense. The active defense is to change the model's outputs so that the attackers can only obtain the misleading information. Then the attackers cannot stealing the target model. However, this kind of approach is very expensive because they need to perform like bad propagations and also like to use like a model ensemble to perform the defense. The passive defense is that for this kind of defense, they can only verify whether the model has been stolen. They cannot minimize the victim model target clone model's performance. So these are passive defense and they cannot reduce the clone model performance. So to address these challenges, instead of like existing words, they are static defense. They don't change the model parameters and only resort to the test time by propagations to change the model outputs. So the benefits of our approach is that it is a dynamic approach, and we change the model parameters during the defense process to minimize the stolen model's accuracy. So the drawback now we compare to the existing work and our work is that for the static defense, they maximally change both the benign and attack queries. So their outputs are maximally changed no matter whether it is a benign query or the attack queries. But this would sacrifice the utility because as we observed in these figures, its utility is maximally reduced for the benign data. But for the attack queries, its defense is not maximally changed because its label is still maintained. However, for our like continual learning defense, we can minimally change the model outputs for the benign queries, but for the attack queries, we can also change even its label. So we can maximally achieve the effective defense.
If you can distinguish between
Yeah.
benign and attack queries,
Mm.
why are you even answering?
Yeah, so actually this is, we cannot distinguish. We can only like use some like surrogate data sets.
So I can distinguish. I
Hmm?
can distinguish, once you answer it like that, I can distinguish.
Actually, is we cannot
But once you answer it like this,
Hmm.
I can distinguish. So you just put a picture there,
hmm,
right? Where you are sending different answers,
hmm,
right?
yeah,
Okay, and you have the other picture above where you are sending the corresponding answers. Once that exists, then I can distinguish. No,
so I think this is automatic process. We cannot use for example, in the ChatGPT, there is a large amount of queries. We cannot use a human to distinguish whether,
no,
Hmm?
but if you can classify it
Yeah.
away,
yeah, right.
which
So,
you can clearly classify once you have what you wrote there, then I can just not answer.
yeah, actually you are right. If you can distinguish it is benign attack queries, then this problem is solved. But actually, this is because of the attack query, it is like kind of like a OD data set or some other mixed like ID and OD data set. We cannot like in ODs, we still cannot to distinguish whether it is or not. So this is just an assumption if you can, but these assumptions actually cannot hold in practice. Okay, yeah. So actually is so here I use the benign queries and attack queries. So it just for to illustrate this point, it is not assumed we can distinguish between the benign and attack query. So the basic approach is that since we assume that we do not know whether it is benign or attack queries, the goal of first approach is a basic active word marking. So in this direction is we add word mark to the input data. The goal is that for the ID data set, after we add word markings to the input data, we want to ensure that its output is only minimally changed. But for the OD data word marking, we want to change even for its label. So the goal is to minimize to maximum the likelihood on the ID data and to maximally change on the OD data set. As we mentioned before, here like for experiment, to ensure that we don't know what is benign data, what is accurate, what is attack query data. So we ensure that the attack data and the OD data are not overlap to ensure that our method can generalize across like when we even don't know whether it is attack or benign data. Now we evaluate the defense performance by the clone model's accuracy with a large scale vision transformer across like different data sets and compared to different defense approach. So like with both soft label and hard labels, we achieve the lowest clone model accuracies. This means that we can maximally reduce the clone model's performance. In the second approach is that so in the Bayesian-based active word markings, this approach can only protect the functionality, but they cannot protect the architecture, the running efficiency. So in these works, we propose the dynamic architectures can protect its functionalities, architecture, and also improve its running efficiency at the same time. So the basic idea is that we use the in-distribution data to exit at later exit points. For example, in a convolutional or transformer network, we let the ID data to exit at a later exit points because this layers attract better representation. But for the OD data set, we let data to exit at earlier exits. This is because the earlier layers, for example, the convolution networks, they extract the non-semantic features. So we let these OD queries to exit at this layers, they can only output like misleading information for the attacker. But using these dynamic architectures, we can achieve like to protect the functionalities, efficiency, and the architecture at the same time. So to evaluate the performance of clone model accuracies, we compare the clone model accuracies across the different data sets and different defense approach. So we can observe that our method achieves the lowest clone model accuracy. So this represents the most effective defense approaches. This is achieves a state-of-art performance across like existing defense method. Now let's discuss the future works. So in my future works, I will develop the to address the safeties and continual learnings in foundation model. For example, I will extend my approach to like multimodality language models and also for the diffusion models. The second direction is like in the biomedical research areas, the trustworthiness is very important because we want this kind of API to make a reliable decision. So I will extend my research approach to the biomedical AI research field by developing the safeties and fairness, robustness improvement. The third directions, I will extend my research in the embodied AI to ensure that the continual learnings will extend to make the physical robotics to achieve like a similar human level intelligence. Like a human, we can incrementally learn different tasks and knowledges over time. I also aim to make the physical robotics can learn self-adaptively with their learned capabilities over time. For the research findings in the futures, I will apply for like NSF and health, medicals, and DARPA DOD, and also possible maybe from industry, but mainly from the government. So for the NSF program, I will apply for the AI, RS, AF, and also for the NSF Career Award. For the health, medicals, I will apply for the NIH, NIA, NIBIB, and also NIGMS. So these future research directions will be applied to this research funding sources. So for the courses, I can teach at these different courses at UCF, like the programming, discrete structures, machine learning courses, algorithm analysis, and so on. This is my published papers in continual learning. And this is my published papers at Trustworthy AI. And also this is a data efficient learning, but not covered today. Thank you for listening. Is there any questions? Okay.
Also was when approached to the book model.
Yeah.
So the fact that model couldn't be properly formed. Those models also have like frequency when approached with it and learn. Make me them forget less what the approaches to reduce forgetfulness as well. What that does testing the defensive capabilities.
Yeah, so I only test its defense capabilities. Yeah, so for the like continual learning large language model is the defense and other tasks maybe like considered simultaneously, but will be left as a future work to explore. Thank you so much. Okay.
Any other questions?
Yeah.
Any
Go ahead.
questions from the?
For the continued learning, so the memory loss function measures the similarity between class A and class B. You're minimizing the similarity, so if you minimize similarity, class A and class B is also minimizing the memory loss.
Actually, I would clarify that this is not to minimize the similarity across the different classes, but is to minimize the similarities across different data points representation. This is to encourage data representation not cluster into a small, to concentrate on like some high density areas, but to encourage the representative to spread out so that they will not very easy. Yeah.
It doesn't always.
I have a question.
It's
That's-
okay. Yeah.
Yeah, so for the kernelized method, for the minimax objective, we treat particles like we treat the buffer samples like particles, like the particles interacting, right? So and if we have the buffer size as n, then the computational complexity will be like O of n square or something, because we have to compute because we treat buffer samples like particles. So how do we optimize the computational complexity in the?
Yeah. This is actually a great question. So, one way is that we can during the early epochs of during the training process, we can let models to optimize by itself. But in the later stage, the model may be more easily to overfit. So during this stage, we can adopt some memory evolutions to update the data samples. So this would reduce the most of the optimization challenges. And we can also to subsample the memory buffer data. For example, if we have 100 or 500 data points, we can subsample a small mini batch 32 examples from the memory buffer and then performs the memory evolutions on these small subsets.
Got it.
Hello?
Thank you.
Thank you so much. Okay.
Loss function objective. There was a second part, n of theta or something.
Sorry.
You had a continual learning objective function that had two parts. There was a second part that had like n of theta or something. Can you please repeat?
So you mean
In
here? Okay.
That-
Yeah.
that-
Yeah, thank you for your question. So the second part of forgetting loss functions, for example, we can use a memory buffer replay loss function. So this loss function represents the loss function summed over the memory buffer. And we can this forgetting loss function can also be considered like a regularization based loss function. For example, we add a regularization to encourage the new data, the new parameters will be close to the previous optimal. Yeah. Yeah, thank you.